Okay, in this video we will look at the basic definitions for formal languages, and let's jump right in. We have 3 definitions: an alphabet, a string, and a formal language. And basically these relate to each other as, exactly in real life. A formal language, a language is a set of words, a set of strings, and strings are made up of symbols that come from an alphabet. So an alphabet is a finite set of symbols. Finite set of symbols, that's the definition of an alphabet. For example, this is an alphabet. It's a set that contains 2 symbols, the symbol A and the symbol B. It's a finite set, and notice sets we write in those curly brackets, and the elements inside the set we separate them by comma. This would be another example for an alphabet that you can use to write words from the English language, just the letters A to Z. Or if you want to talk about calculations, you can use this alphabet that contains some mathematical operations and some digits. Okay, so I guess it's clear what an alphabet is. So what is a string? A string is a finite sequence of symbols from an alphabet. So if AB is our alphabet, then we could write the following: string ABBA, ABBA. This is a string over this alphabet. If we use this alphabet, we could, for example, write the word hello. If we use this alphabet, we cannot. This word hello is a string over this alphabet, but not over this alphabet. Okay, and let's make one example for this alphabet. For example, this sequence 1 + 9 - times plus. This is a string that doesn't make sense, but strings don't have to make sense. A string is just any finite sequence of symbols over this alphabet. So this is also a string over this alphabet. Strings have some properties, like the length. This first string, for example, has the length 4 because it consists of 4 symbols. This has length 5. This has length 7. It's also possible to have a string of length 1. Just one symbol. For example, this A is a string over this alphabet. There is even a string of length 0. This at first maybe this might sound a little strange, but think of it in the programming languages. You can define strings that have length 0, empty strings. And this also exists in the theory of formal languages, and we will denote it by epsilon. So epsilon is the string of length 0, and there's only one such string. Also notice that in an alphabet, the order how you write it doesn't matter. This AB is actually the same alphabet as the alphabet BA. The order doesn't matter, and also if you write one symbol multiple times doesn't change the set. So this would even be the same as the set A, B, but nobody would write that, doesn't make sense. So in an alphabet, the order of symbols doesn't matter, it's just a collection of symbols. But for strings, the order does matter. For example, ABBA, that's a band. But if you write, for example, AB, it has the same letters, but in another order, that's not a band anymore, as far as I know. So, these are 2 different strings. ABBA and ABAB are 2 different strings. They have the same length, they contain the same letters, but in a different order, so they are not the same string. Okay, and now what is a formal language? A formal language is a set of strings. Okay, let's make an example for a language over this alphabet AB. For example, this is a formal language over this alphabet. It contains 4 words: the word ABB, the word B, the empty word of length 0, and the word AAAAAB. And it's also important that if we have a formal language, that all the strings are made from the same alphabet. So this is a formal language over the alphabet AB. But formal languages don't have to be finite, There can be infinite sets of strings. Let's make an example, maybe with this alphabet, yeah, you could write something like this: e to the n with n from the positive integers. If you're not familiar with this notation, this means the words have this form, and then there's this line, and after there's a condition. So the condition is n is a natural number, positive integer, or including 0 maybe. So this could be written as, well, e to the 0 should be the empty word, and then e, triple E, and so on. So words that consist only of e's, every single word inside here consists of a finite number of e's, but there are infinitely many words inside this language. Okay, I want to give another example, also introducing a new notation, that is the star notation. If we take a set, like, for example, this alphabet, and we write a star here, this means all possible finite sequences that you can create from these symbols. So this would be the empty string, and the string A, and the string B, and all combinations of length 4, that is AA, AB, BA, and BB, and all combinations of length 3, yeah, and so on. Yeah, all combinations of finite length. Remember, strings are always finite in our context, but formal languages can be infinite. They can contain infinitely many strings. Okay, and if these examples all seem very strange to you, like you cannot think why that should be useful, I want to give another example. Yeah, consider this alphabet. The symbols here consist of several letters, but let's accept that for now. One symbol is if, one symbol is condition, one symbol is then, we have statement, else, and, yeah. What strings can you make up from these symbols? Yeah, for example, this if, condition, then, statement, and. Yeah, this would be a word consisting of 1, 2, 3, 4, 5, 6 symbols. This is one word or one string of length 6. And of course, you see now this can be used to describe programming languages. Yeah, so Java, for example, or pick your favorite programming language, is just a formal language. Yeah, you just have to choose the right alphabet, and you have to define how do the syntactically correct strings look like, the syntactically correct programs look like, and then you can treat programming languages just like formal languages. Yeah, so this is one application of formal languages. Okay, I hope everything is clear about these alphabet, string, and formal language. If you have any question, you can write comments on the video, and in the next video we will define finite state machines, deterministic finite automata.